dissect this UL2 paper. It claims to create a universally effective language model, working across diverse data sets and setups. What's the core innovation here, from your perspective? What problem does it solve that existing models don't?
The core issue is the lack of a truly universal language model. Current models often excel at specific tasks, like T5 for translation or GPT for generation, but struggle to generalize. UL2 tackles this by unifying different pre-training paradigms rather than sticking to a single approach. It's not just about architecture, encoder, keycoder versus decoder only, but also about the objectives used during pre-training.
So existing models are task-specific in their architecture and training objectives. How does UL2 decouple these two aspects?
Exactly. UL2 argues that the architecture choice, encoder, decoder, decoder only, is secondary to the pre-training objective. They show that their unified approach, Mixture-of-Denoisers mode, works well with both architectures. The key is the mode objective.
Let's talk about MADE. What's the intuition behind mixing different denoising objectives? Why not just stick with one proven method?
The intuition is that a truly universal model needs exposure to diverse problems during pre-training. Mode combines several denoising objectives: R, denoising, standard span corruption; S, denoising, sequential denoising, similar to prefix language modeling; and X, denoising, extreme denoising with long spans and high corruption rates. Each objective presents unique challenges, forcing the model to learn different skills. A single objective might lead to over-specialization.
Interesting. So X denoising in particular seems designed to push the model's boundaries. What are the specific benefits of this extreme approach? What are the trade-offs?
X denoising aims to bridge the gap between span corruption and language modeling. By using long spans and high corruption rates, it forces the model to generate long, coherent text from limited context, a skill crucial for many tasks. The trade-off is increased computational cost and potential instability during training. However, the paper shows that the benefits outweigh the costs.
The paper also mentions mode switching. How does this mechanism enhance the model's performance? Is it simply a clever prompting technique?
Mode switching is more than just prompting. During pre-training, UL2 uses Sentinel tokens to associate different pre-training schemes with specific modes. During downstream fine-tuning, these tokens allow the model to dynamically switch between modes, adapting its behavior to the specific task. It's a way to leverage the diverse skills learned during pre-training.
The paper reports SOTA results on a massive number of tasks. How robust are these results? Are there any limitations or caveats to consider?
The results are impressive, achieving SOTA on many tasks across various categories: generation, understanding, reasoning, etc. However, the 20B parameter model is still relatively modest compared to truly massive models like Palm 540B. Also, the pre-training data C4 is less curated than datasets used by some competitors. Despite these limitations, UL2 consistently outperforms established baselines, suggesting the approach is promising.
The paper highlights a significant improvement over T5 and GPT-like models. Can you quantify this improvement and discuss the reasons behind it?
UL2 outperforms T5 by an average of 43.6% and GPT-like models by 76.1% across 9 diverse tasks. This improvement stems from the unified pre-training objective, Mode D, and the mode switching mechanism. Mode D provides a broader skill set, while mode switching allows the model to adapt to different task requirements.
The authors also explore scaling UL2 to 20B parameters. What were the key findings from these large-scale experiments? Did the performance gains scale linearly?
The 20B UL2 model achieves SOTA on over 50 NLP tasks. While the paper doesn't explicitly discuss linear scaling, the results suggest that the benefits of Mode D and mode switching extend to larger models. However, they acknowledge potential limitations due to training instabilities at this scale.
The paper also investigates chain-of-thought prompting with UL2. What are the implications of this finding?
This is significant because chain of thought prompting, previously thought to require extremely large models, works effectively with the 20B UL2 model. This suggests that the Mode D objective might contribute to the emergence of reasoning capabilities at a smaller scale.
Finally, the authors apply Phelan instruction tuning to UL2. How does this further enhance the model's capabilities?
FLAN instruction tuning improves UL2's performance on MMLU and Big Bench, making it competitive with much larger models like FLAN PALM 62B. This demonstrates the adaptability and potential of the UL2 architecture.
Given the results, what are the key takeaways for practitioners? What are the potential applications of UL2?
UL2 offers a promising approach for building more universal language models. Its unified pre-training objective and mode switching mechanism lead to improved performance and generalization across a wide range of tasks. Potential applications are numerous, spanning various NLP domains where a single versatile model is desirable.
Are there any limitations or future research directions you see as particularly important?
Further research should focus on scaling UL2 to even larger models and exploring more sophisticated mode switching techniques. Investigating the interplay between MACHI and emergent abilities like chain of thought reasoning is also crucial. Finally, exploring different pre-training datasets beyond C4 could further enhance performance.
This has been a very insightful discussion. Thank you for sharing your expertise.